Hello, and welcome to my course project presentation on the synthesis of eugenol, as we use plants as medicine. What is eugenol? Today we will dive into the making of eugenol, or the synthesis of eugenol. But what is it? Eugenol is a volatile, colorless to yellowish liquid, and is mainly found in essential oils. Eugenol is a primary compound of essential oils, such as clove oil, which is extracted from dried flower buds, leaves, or barks of certain trees. Eugenol is used as an antiseptic, anesthetic, and to relieve pain. It is also used in dentistry to numb gums and to treat cavities. Now that we have a grasp on exactly what eugenol is and how it's used, we will further break down why we want to synthesize this molecule and use it in further drug discovery. Our plan is to utilize a faster, more efficient synthesis that produces an outcome with better, longer-lasting results and fewer, less harmful byproducts during its production. In this flyer, you will see a breakdown of the 5-step synthesis method we plan to use to make this happen. For the first step, we will discuss the halogenation of guaiacol. This step is a chemical reaction where a halogen, like chlorine or bromine, is added to guaiacol, a naturally occurring compound found in clove oil. This reaction happens because guaiacol has a benzene ring with an oxygen containing groups that make it more reactive towards halogens. When a halogen is introduced, often with a catalyst like iron or chloride, it attaches to a specific position on the benzene ring, depending on the reaction conditions. This process is useful in making pharmaceuticals like eugenol. We will be using IR spectroscopy for this, which will confirm the introduction of the halogen by detecting changes. Electron flow involves activation of the halogen, nucleophilic attack on the benzene ring, resonance stabilization of the rhenium ion, and reformation of aromaticity. For the second step in this synthesis, we discover alkylation reaction, which is a chemical reaction where an alkyl group is added to another molecule. In the case of guaiacol, this happens when it reacts with an alkyl halide in the presence of a catalyst. The catalyst helps to break the alkyl halide apart, creating a reactive alkyl fragment that easily attaches to the guaiacol's benzene ring. This reaction is useful for modifying natural compounds to create the final product of eugenol. The IR spectroscopy will detect the alkylation. The electron flow for this step involves the formation of the electrophile, the nucleophilic attack by the aromatic ring, resonance stabilization of the rhenium ion, and restoration of the aromaticity. For step 3, we take a closer look at the Grignard reaction, which is a chemical process used to build larger molecules by adding carbon groups to other compounds. It involves a Grignard reagent, which is made by reacting a magnesium metal with an organic halide. This reagent acts as a highly reactive carbon tool that can attach to a carbonyl compound, forming new carbon-to-carbon bonds. This reaction is widely used in making pharmaceuticals like eugenol. Electron flow for this step involves the formation of a Grignard reagent, nucleophilic attack on the carbonyl carbon, formation of the alkoxide intermediate, and protonation. IR spectroscopy is used to detect the introduction of the allyl group. For our fourth step, we discuss deprotection, which is a process that removes the alkyl group from a molecule to restore its original functional group, usually using acids or special reagents. For example, if a hydroxyl group was protected as OCH3, acids like HRBr break the bond, freeing the OH. This step is crucial in chemical synthesis, especially in making medicines like eugenol. The IR spectroscopy identifies the reappearance of the hydroxyl sketch. Electron flow involves the protonation of the ether oxygen, cleavage of the CO bond, and formation of alcohol and alkyl halide. Our final step is purification and isolation of eugenol, and it involves separating it from other substances using extraction, distillation, and crystallization. First, a base dissolves eugenol in water by temporarily changing its chemical form. Then an acid restores it to its natural state. Next, distillation gently creates heat in the mixture, turning eugenol into vapor. which is then cooled back down into a purified liquid. Finally, crystallization helps to further purify it by slowly solidifying eugenol from a solvent. These steps ensure we get a high purity eugenol for its use in medicines. Electron flow involves acid-base extraction, distillation, and crystallization. Final formation of eugenol is done using our instrument of IR spectroscopy, which verifies the presence of characteristic functional groups. For this particular synthesis of eugenol, the 5-step method introduces us to halogenation of glycol, alkylation reaction, the addition of an allyl group, the removing of an alkyl group, and the purification and final acylation of eugenol. This approach optimizes selectivity and minimizes undesired side reactions, making it a reliable method for eugenol production. And then we have my references. Thank you so much for listening.